In section 5.2, we're going to talk about the bisectors of triangles. So who uses this? An event planner can use perpendicular bisectors of triangles to actually find the best location for a fireworks display. So since triangles have three sides, it has three perpendicular bisectors. When you construct the perpendicular bisectors, you find that they have an interesting property. Now, we are not going to construct this, but I'm just going to show you what happens here. If you drew a scalene triangle that has acute angles on a piece of patty paper, it's like tracing paper, and then you fold the perpendicular bisector of each side, and you don't need to write this down, but like let's say right here, the bisector. So the bisector of this side is right here. You folded the paper, and you kept doing that. And so right here you can see your folds. What do you notice about all three perpendicular bisectors? They intersect at a point, and they called this point P. When three or more lines intersect at one point, the lines are said to be concurrent. So concurrent is when the three or more lines intersect at one point. The point of concurrency is the point where they intersect. In the construction, you saw that the three perpendicular bisectors of a triangle are concurrent because they all intersected at a point. That point of concurrency is called the circumcenter of the triangle. So here is the circumcenter theorem. The circumcenter theorem of a triangle is equidistant from the vertices of the triangle. So this theorem states that PA would be equal to PB, which is equal to PC. So what happens is this. Perpendicular bisectors. Now, the red lines represent the perpendicular bisectors. They all meet at point P. That is called the point of concurrency. This circumcenter of the triangle, which is point P, is going to be equidistant to all the vertices of the triangle. So you connect the corner, or the vertices, A to P, B to P, and C to P, and they are all equal. Notice they're not congruent, they are equal. So the circumcenter can be inside the triangle, outside the triangle, or on the triangle. As you can see here, an acute triangle would have them on the inside, an obtuse triangle has them on the outside, and a right triangle has the circumcenter on the triangle. The circumcenter of triangle ABC in this case is the center of its circumscribed circle. A circle that contains all the vertices of a polygon is circumscribed about the polygon. So this is circumscribed about the polygon, which is the triangle. All right, example 1. Now, once again, this is a really easy problem. You do not have to do a proof or anything, but I'm going to actually write down the steps that you would have to write if this was a proof. So what are we given? We're given that KZ, LZ, and MZ are all the perpendicular bisectors. So we know they're all perpendicular bisectors of the big triangle. I want to find HZ. Now, you're probably thinking that's really easy, because if you look, we know HZ has to be equal to GZ, which has to be equal to JZ. So, because we know GZ is the same as HZ, we know it's 19.9, but let's write this. So what you would have to state is, we have to first state that Z is the circumcenter of triangle GHJ. So by the circumcenter theorem, we know Z is equidistant from the vertices of triangle GHJ. So we would have to state that Z is equidistant from the vertices. That's why is that? Because circumcenter theorem. So we could say this. So this is what you'd write down. HZ is equal to GZ. Now, if you wanted to find ZM as well, you could put equals ZM, but we don't need to find that. What's the reason behind this? This is the circumcenter theorem. We know they're all equal. Since we know GZ is 19.9, we use substitution, and there's my answer. HZ has a length of 19.9. Example number 2, finding the circumcenter of the triangle. I want to find the circumcenter of triangle RSO with vertices, and they give you the vertices. Well, step 1 is going to be graphing the triangle. So if we graph them, negative 6, 0, that's R, 0, 4 is S, and 0, 0 is O. So we want to find the circumcenter. So what we have to do now is we have to draw our perpendicular bisectors. So we have to find equations for two perpendicular bisectors. Now, since two sides of the triangle lie along the axis, we can use the graph to find the perpendicular bisectors of these two sides. The perpendicular bisector of segment RO, well, it has to bisect it, and it has to be perpendicular. We know we have a slope of 0 here. We know this is 6 units, so we know the perpendicular bisector would actually go right through negative 3. So we know one perpendicular bisector would be the equation x equals negative 3. Now, along this side, we know this is 4 units, the vertical side of the triangle. Well, half of 4 is 2, so we know, since it's perpendicular, we know our line for this perpendicular bisector would be y equals 2. So we found the intersection. The intersection is here. Now we could do the third side, but it's going to cross right through there. So once again, it's a right triangle. So since it's a right triangle, the circumcenter is on the point. So the point here would be negative 3, 2. So the circumcenter would be your final answer of negative 3, 2. A triangle has 3 angles, so it has 3 angle bisectors. So now we're going to talk about the angle bisectors. The angle bisectors of a triangle are also concurrent. The point of concurrency for angle bisectors, remember, we've already talked about the point of concurrency for segment bisectors. We're now talking about angle bisectors. This is called the incenter of the triangle. The incenter of a triangle is equidistant from the sides of the triangle. So here's what it states. The incenter of a triangle is equidistant from the sides of the triangle. The lengths of px is equal to the length of py, which is equal to pz. So let's look at our picture and figure out what in the world does this mean. We're talking about angle bisectors. The red segments represent the bisectors of each of our 3 angles of the triangle. So angle A, B, and C are all bisected. If we connect them, they all connect at point P. The incenter is that point. Now, it's equidistant from all the sides. So that means all of these blue sides are all equal. Now, these are not perpendicular bisectors. They're perpendicular. You'll notice, though, that these do not bisect the sides. They are only equidistant to form 90-degree angles, but they're equal. Now, unlike the circumcenter, the incenter is always inside the triangle. Acute triangle, obtuse triangle, right triangle. Now before we had an inscribed polygon. Now we have the incenter is the center of the triangle's inscribed circle. So now we have a circle inside the triangle. A circle inscribed in a polygon intersects each line that contains a side of a polygon at exactly one point. So think of it this way. The incenter is when we have, when you have that as a circle inscribed in a polygon. And a circumcenter is when we have a polygon circumscribed with a circle around it. Let's look at example 3. Segment JV and segment KV are angle bisectors of triangle JKL. So what I would do is I would actually mark them in the picture. We know they're angle bisectors. Find each measure. So the first one is I want to know the distance from V to KL. So V to KL. So if I drew that in, remember, it's not going to be bisecting it, but it will be perpendicular. So what do we notice? Well, we could write this down, that V is the incenter, since V is the incenter, and by the incenter theorem, we know this. We know that VW would have to be equal to all of the other segments formed by the incenter. So let's look at our picture. VW has to be equal to this green line, which would also have to be equal to the segment that's equidistant to this side. So our point is equidistant to all three sides. So we know VW, because of the incenter theorem, would have to be also 7.3. So the distance from V to KL is also 7.3. So now we want to do the measure of angle VKL. So VKL is right there. And actually, let's write this whole thing. I'm going to move this up. Let's write, I'm going to get rid of that, move this up. Let's write this whole thing down as if you were writing a proof. So let's start with what we know. We want to find that angle measure. Now you're like, oh, I don't remember what rule do I use? I don't remember seeing that. Remember though, you have a big triangle. And you can still figure this out without doing any of the concepts really in this chapter, but using what you know from previous chapters. We know that the measure of angle K, so watch this, measure of angle KJL, this is where I'm going to start at, is KJL, this angle right here. And why? Because I'm given that this is 19 degrees. So the measure of angle KJL is going to be equal to twice the measure of angle VJL. Now why do I use that? Because I'm given that that's 19 degrees. What's the reason? The reason is because JV is the bisector of KJL. We know it's the bisector. It says it. So you would say definition of angle bisector. So we can substitute in the measure of angle KJL is going to be twice the measure of angle VJL, which is 19 degrees. So the measure of angle KJL would equal 38 degrees. Now, we know this angle. We know this angle. Let's find the other angle. It's just the triangle sum theorem. So because of the triangle sum theorem, I know that the measure of angle KJL plus the measure of angle JLK, which is 106, plus the measure of angle JKL, all equals 180 degrees. Now we use substitution. We know this one's 38 degrees. We know this one's 106 degrees. We do not know this one, the measure of angle JKL. And now we solve this. We add those together by subtraction property. The measure of angle JKL is equal to 36 degrees. Then we could say the measure of angle VKL is going to be half the measure of angle JKL. Why is that? Because definition of angle bisector. So the last step, the measure of angle VKL is half of 36, which is going to give us 18 degrees. All right, example 4, you do not need to write this down, just pay attention. For the next 4th of July, the towns of Ashton, Bradford, and Clearview will launch a fireworks display from a boat in the lake. Draw a sketch to show where the boat should be positioned so that it is the same distance from all 3 towns. Justify your sketch. So I have the answer already here, but let the 3 towns be vertices of a triangle. So we would connect them, making a triangle. Now, if we want to know that the distance to all the towns are the same, if we look here, we're going to have to draw our circumcenter. By the circumcenter theorem, the circumcenter of the triangle is equidistant from the vertices. Make sure you understand that. It's confusing, and it can be easy to get confused, the incenter and circumcenter. The circumcenter is when you draw your perpendicular bisectors and your point is going to be equidistant to all the vertices, not the sides. That's the incenter. So you would then draw all of your perpendicular bisectors of each side, and they would cross here at point F. Now if I connected these, this would prove that F is equidistant from all the vertices, which happen to be all of the towns. So the boat should go at point F, which is the circumcenter. Your vocabulary are concurrent, point of concurrency, circumcenter of a triangle, circumscribed, incenter of a triangle, and inscribed.